Hello boys and girls. Today we are going to discuss about production, propagation and graphical representation of sound. Have you ever wondered what exactly sound is? Yes, sound is a form of energy which has the capacity to do work. Here we can see that the sound energy is being converted into electrical energy. Until now we have studied that sound is which type of wave? Mechanical or a non-mechanical? Yes, sound is a mechanical wave, and to be more precise, we can say that it is a longitudinal wave in which the medium particles they oscillate back and forth about their mean position and the disturbance is carried forward. But now the question arises, how is the sound produced? Also, how does sound propagate in a medium? And more importantly, how do we graphically represent the sound waves? So let us try to seek answer to these questions in this module. Here we have a guitar, a metallic bowl and a tuning fork. Now just pluck one of the strings of the guitar. How did you find the sound so produced? Wasn't it a melodious sound which is soothing to hear? Okay. Next, now we just hit the metallic bowl with a stick. This time we hear the sound of a different quality. Now let us just hit the prongs of a tuning fork with an object like a rubber ball and bring it closer to the ears. And what happens in this case? This time just a faint sound is heard. But if we touch this tuning fork with a ping pong ball suspended by a thread from a support, what do we see? We can see here that this ping pong ball is thrown to one side, it comes back, hits the prong and then moves away. And then this is repeated again and again. So when we closely look at these three objects, we find that each of these objects are actually set into vibrations whenever they are hit or plugged. Now if we see the slow motion of this tuning fork, we will actually find out how this tuning fork is vibrating or how the metallic bowl started vibrating when it was hit by a stick and how the strings of a guitar they also vibrate when they are plugged. So from all these activities that we have conducted so far, we've understood that sound is produced by a vibrating body. And these vibrations can be produced by either plucking or scratching or hitting different objects. Now let's do an activity to increase our understanding of production and propagation of sound waves. So now we fill an empty glass with some water and we dip the prongs of tuning fork in it. Do we notice something happening in the water? Well, not really. Okay, so now let's repeat the same activity with the vibrating tuning fork. And the vibrations are set into the tuning fork. Now we gently touch the water surface with one of the prongs of the vibrating tuning fork. And what do you observe this time? We can see here that the water surface, it gets lightly agitated and some water droplets are formed on the glass surface. And some of the water droplets, they may even come out of the glass. And now what will happen if we dip both the prongs of the vibrating tuning fork in water? Well, in this case, the water surface, it gets strongly agitated. And we can notice here that due to this strong agitation, some water droplets, they even come out of the glass. And now the question that you all would be waiting to ask me is that, okay, now we know how sound is produced, but then how does the sound produced by a vibrating body propagates through a medium? For this, again we once again take a tuning fork. When we hit the prongs of the tuning fork with the rubber ball, what do you observe? If we closely observe the prongs, we will notice really fast repeating oscillations taking place. And if we notice these fast oscillations in a slow motion, then what do we see? We see that the prong it goes outwards, reaches a maximum point, and then it comes back and reaches maximum on the opposite side. Now, when it does that, that is the tuning fork, when it begins to vibrate, then what happens to the surrounding air? We know that there is air all around us, and when the prongs, they move outwards, it starts pushing and compressing the air in front of it. And do you know what happens when the vibrating prong, it reaches to a maximum point? When the vibrating prong, when it reaches to the maximum point, it creates a region of high pressure. And this high pressure region, it starts to move away from the vibrating prong. When the prong, it comes back, it pulls the air behind it, creating a region of low pressure. So what is this prong actually doing in one back and forth motion? It pushes and compresses the air in front of it, thus creating a region of high pressure, and when it comes back, then it creates a region of low pressure. Now, what do we call these high pressure and low pressure regions? The region of high pressure is known as compression, and the region of low pressure is known as rarefaction. So there will be a series of high pressure and low pressure areas, and what will the prong do now is that it will create this back and forth motion again and again, and consequently the air particles present in high pressure region, they will hit the neighboring particles, compress the air again, and in this way the compression moves forward, followed by rarefaction away from the vibrating object. So what do you observe when the prong moves back and forth rapidly? As the prong moves back and forth rapidly, a series of compressions and rarefactions is created in the air. These in turn make up the sound waves that propagate through the medium. Now in this figure, I'm showing basically that sound waves are traveling in forward direction. But does sound actually travel in one specific direction? The answer is no. As we all know that air is all around us, so the sound can actually travel in all the possible directions. Now imagine if you're writing your physics paper and there's a question asked to you to represent the sound waves graphically. So how will you do that? Don't worry. All you have to do is just recall the tuning fork experiments and the slinky experiments that we did in the previous module, and you'll be able to have a correct representation of the sound wave in your paper. So here I will make it for you. Again, we once again take a tuning fork. When we hit the prongs of the tuning fork with the rubber ball, what happens? The prong, it starts to vibrate. Simple. When the prong, it moves in the forward direction, it creates a high pressure area. So how will you show these regions in a graph? We can show the high pressure area with the upper portion of the curve. And the peak in this upper portion, it represents the region of maximum compression, and it is called the crest. Now the prongs of the tuning fork, they come back creating a region of low pressure. And we can show the low pressure area with the lower portion of the curve. And the peak in the lower portion representing the minimum pressure is called the trough. Similar is the case with the slinky. The expression or the compression where the rings are crowded together is represented by the upper portion of the curve, and the portion where the rings, they are spread apart, it is represented by the valley or the lower portion of the curve. Now as these disturbances, they keep on moving forward as the sound propagates, so there will be a series of compressions and rarefactions which are going to be formed, and this can be represented in the graph like this. Now if you look at this graph, isn't it giving us a feel of a transverse wave? But this graph actually shows the variation in the air pressure during propagation of sound waves, and this is with respect to time. So on the y-axis we have the change in the air pressure, whereas on the x-axis we have time. So we see that both the transverse and the longitudinal waves can be represented in a similar manner on a graph. The difference is that in a transverse wave, a crest is a point where the displacement of the medium particle from the mean position is at a maximum, and the trough is a point which is the lowest point of the wave, representing the maximum displacement in the opposite direction from the mean position. While in case of the longitudinal wave, we have the compressions and the rarefactions. Now friends, before we close down on this module, I have a small trivia for you all. Now that we've already had a brief understanding of the graphical representation of sound waves, so some of you might be thinking that are sound waves always of this shape, or can they be of some other shape as well? How many of you have this doubt? Okay, well, we can see, and we've just learnt also, that sound waves are simply propagating changes in pressure, and so they can take any form, including completely random shape also. This is just one of the shapes which is sinusoidal here. But then there can be triangle and square sound waves as well. Now the same wave, it can be represented in various shapes, and this makes our analysis really difficult. So we often model the sound as a set of superimposed sinusoids, and this is done by using a mathematical technique called Fourier analysis. Don't worry, this is a concept which you will be learning in your higher grades. And for now, you can simply keep this graphical representation in your mind when it comes to visualizing the sound waves. So with this, we come to the end of this module on production, propagation, and graphical representation of sound. Thank you.